Hi everyone, can you hear me? Awesome. So my name is Joshua Lind, and today I'm going to be presenting Teechain, a secure payment network with asynchronous blockchain access. So Teechain is a collaboration between the Large-Scale Data and Systems Group at Imperial College in London and the Initiative for Cryptocurrencies and Contracts at Cornell University and the Technion in Israel. So the problem today is that blockchains aren't scaling. Consensus is slow, and all nodes must agree on all transactions. For example, in Bitcoin, Nakamoto consensus limits the throughput of the entire network to around 4 transactions a second, and transactions take tens of minutes to be written to the blockchain. This leads to a natural concern. Will we ever be able to scale to the throughputs of the payment processes that we see in the real world? Well, one interesting research direction is off-chain payment networks. Payment networks allow parties to pay each other directly without writing to the blockchain. Instead, parties manage their funds and their balances themselves. So payment networks do this by forming point-to-point payment channels between parties. And each payment channel supports bidirectional payments between the two endpoints in the channel. Payment networks also support multi-hop payments, where two parties can pay each other indirectly via a number of intermediaries. So how exactly do these payment channels work? Well, payment channels operate in 3 phases. In the first phase, one or both parties writes a deposit transaction to the blockchain, and a deposit is a set of funds associated with the payment channel. Next, the parties can pay each other directly, spending from their deposits, and each payment updates the balances of the two parties. This all occurs off-chain. Finally, one or both parties can decide to terminate the payment channel by writing the final balance down to the blockchain, and we term this channel settlement. Now, an issue arises here. How do you ensure that the correct balance is written to the blockchain? For example, what happens if Bob misbehaves and writes an old balance to the blockchain in order to perform a rollback attack? Well, existing solutions solve this problem by using the blockchain as the root of trust. Essentially, both parties will monitor the blockchain to watch each other for misbehavior. And if one of them misbehaves by writing an old balance, the counterparty will see that old balance and react within a bounded reaction time delta by writing the correct balance down to the blockchain in order to invalidate the rollback attempt. Now, the problem with reaction times is that they require synchronous blockchain access. That is, they assume that parties can read and write transactions to the blockchain within a bounded time. But as we know, blockchains are best effort, and they don't give you any read or write latency bounds. For example, in Bitcoin, if you look at the amount of time it takes to write a transaction to the network, this varies greatly, and latencies can spike. For example, in early 2018, there was a spam attack on the Bitcoin network, which meant that transactions took longer than 7 days to be written to the blockchain. In fact, this is only one of the many different ways in which attackers can manipulate read and write latencies for blockchains. So the question becomes, what value do we use for our reaction times? Well, unfortunately, there's a trade-off. If you have a large reaction time, it makes it harder to attack, but it gives you much slower access to your funds. And if you have a small reaction time, it makes it easier to attack, but it gives you quicker access to your funds. So in order to avoid this, we propose Teechain, the first payment network that operates with asynchronous blockchain access. That is, it makes no assumptions about blockchain read or write latencies. Now, to give you an idea for how Teechain works, I'll present 3 of the challenges that we faced. The first challenge is the need to remove the blockchain as the root of trust during payments. And for this, we introduce a new root of trust called a treasury, which effectively prevents misbehavior in payment channels. Next, we'll discuss how we realize treasuries in the context of a blockchain. And to do this, we combine decentralized committees with trusted execution to form secure treasury committees. Finally, we'll discuss how we maintain consensus within each treasury committee. And here we propose a new variant of chain replication. So for the first challenge, removing the blockchain as the root of trust. So here we introduce a new root of trust called a treasury. Now, a treasury controls funds and balances in payment channels. It effectively mediates between the two parties and prevents misbehavior, and it only ever settles a payment channel once at the correct balance. So in the case of Alice and Bob, Alice will write her deposit down to the blockchain, sending her funds directly to the Treasury. The Treasury can then manage balances of the payment channel, handle payments, and when we come to settle the payment channel, the Treasury will return a single transaction at the correct final balance for the payment channel, and this can then be written to the blockchain. So what you note here is that because you can't perform a rollback attack, there's no need for reaction times. And because this final balance can be written to the blockchain in unbounded latency, you achieve asynchronous blockchain access using a treasury. But the question becomes, how exactly do we realize these treasuries in the context of a blockchain? And this brings us to the second challenge. Specifically, we want to design our treasuries to avoid absolute trust, to avoid centralization, and to be able to integrate with most existing blockchains today. Well, we propose using committees. Now, committees are a general solution that have been well studied for blockchains. They are decentralized in nature because they distribute the role of a single entity to multiple different entities. And they provide a natural fault tolerance to different types of failures. So we propose forming treasury committees, which are a selection of n different parties in the network, where a subset of the committee, M in this case, must agree before access to funds can be granted. And to do this, we use M out of n blockchain transactions to secure deposits. So in the case of Alice and Bob, Alice will write her deposit down to the blockchain using a 3 out of 4 blockchain transaction that requires 3 out of the 4 members in the committee to sign any new transaction that spends the deposit. The committee can then manage the balances between them, handle payments as before, and when we come to settle the payment channel, any 3 of the 4 members can sign the final settlement transaction for the payment channel. So this is good because it means that trust is distributed, and we now require at least M different members to collude before the deposit can be stolen. But the question becomes, how large should M and N be? Well, existing solutions argue that you want to have large committees. You want to make it as difficult as possible for parties to collude in order to violate security. But this brings us back into the ballpark of needing to maintain consensus at a large scale, which we know is difficult and slow. So instead, we propose using trusted execution as a way to reduce the size of committees. Now, trusted execution offers confidentiality and integrity guarantees for code and data. It allows you to effectively trust a hardware implementation instead of a third-party person. Now, I'm sure many of you are aware, but trusted execution environments have been around for a while, and there are various different implementations available. For those who aren't aware, we'll take a quick look at one of these, Intel SGX. So Intel SGX provides confidentiality and integrity guarantees for enclaves. It effectively protects the enclave using hardware access controls, and it isolates it from the rest of the software in the system. In addition, it also offers you hardware protection against physical attacks. So assuming an attacker has physical access to the machine, if the CPU package is not breached, an enclave can maintain its security guarantees. So we propose using trusted execution as a way to secure committee members. And this effectively increases the cost of attacks. So attackers now need to violate trusted execution before they can misbehave within a committee. And we argue that this is actually a practical deployment model for trusted execution environments, because as many of you know, current implementations are vulnerable to a number of different attacks. For example, the foreshadow attack, which recently showed how to use speculative execution to violate security guarantees in Intel SGX. So we combine here trusted execution with committees to leverage a defense-in-depth approach. And this is nice because it gives parties a configurable security model for each deposit. Not only can they decide the values of M and N for themselves, but they can employ trusted execution heterogeneity. That is, they can combine different types of trusted execution technologies together to protect themselves from centralization and specific types of attacks. And this allows them to weigh up the risk to their deposits. So as the value of their deposit increases, so can the size of their committee, as well as the heterogeneity they employ. So this brings us to the third challenge. Having formed our committee, we now want to maintain agreement within that committee. Specifically, we want to do this within a peer-to-peer network where not all nodes are fully connected. So here we propose using chain replication. Now, chain replication offers strong consistency using a chain topology. And it's efficient because it allows you to update the entire chain in order n messages, which is ideal for a peer-to-peer network. So in the case of Alice and Bob, on an update to the payment channel, the update will propagate down all members in the chain to update the committee. Now, of course, if you apply chain replication naively to this scenario, you're going to open yourself up to different types of attacks. And so in our paper, we introduce a new variant of chain replication called force freeze chain replication. Now, due to the time, I can't go into this, so I defer to the paper for details. And there are additional details that we can't discuss in this presentation, such as multi-hop protocol and our ability to support dynamic fund deposits, that is, add and remove funds dynamically to payment channels. So if this interests you, please see our paper. So we implemented Teechain for Bitcoin using Intel SGX, and we have an open source release available online. For our evaluation, we wanted to answer 3 fundamental questions. How well do payment channels perform? How well do multi-hop payments perform? And does Teechain scale out in a payment network deployment? Now, I'll only present some of the key results here, but our baseline comparison is the state-of-the-art Lightning Network, which is a payment network for Bitcoin that requires synchronous blockchain access. So for the first question, how well do payment channels perform? To measure this, we construct various different payment channels between London and New York, and we measure both maximum throughput and latency for payments. In the case of Teechain, we vary the sizes of committees, with the n different members scattered across 3 locations around the world. In terms of throughput, we see that the Lightning Network maxes out at around 1,000 transactions a second. And this comes as a result of the fact that it must execute multiple message exchanges per payment. Teechain, with a committee size of 1, that is offering limited fault tolerance, gives you about 130 times this throughput. Now, as soon as you have 2 or more members in your committee, throughput becomes limited at around the 33,000 transaction a second mark. And this comes as a result of the fact that throughput is limited by the CPU when executing chain replication. Now, in terms of latency, we see that the Lightning Network executes the payment in around 400 milliseconds. Whereas for Teechain, latency grows proportional to the length of the chain. So with about 3 members protecting each deposit, Teechain offers similar latencies to the Lightning Network. So for the second question, does Teechain scale out in a payment network deployment? Here, we take various payment networks, and we replay the Bitcoin transaction history across nodes in our graph. We look specifically at 2 overlay topologies, a complete graph and a hub-and-spoke graph. For the complete graph, we note that every node has a payment channel with every other node, which means there's no need for multi-hop payments. We vary the number of nodes in the graph, and we see that throughput scales pretty linearly with the number of nodes. Interestingly, there is little difference between having 3 or 4 committee members per deposit, and this comes back to the result that we saw earlier. Throughput is limited by the CPU when executing chain replication. We achieve around 1 million transactions a second here using 30 machines in this experiment. Now, for the hub-and-spoke model, we deploy 20 different nodes of various different sizes. And the size of a node dictates its connectivity in the graph, as well as the number of payments it's responsible for executing. So in our paper, we propose a new optimization called temporary channel creation, which effectively allows 2 nodes who have a payment channel to spawn additional channels between them when they undergo high payment congestion. So we use this optimization in our experiments between large and medium nodes. And we vary the maximum number of temporary channels that these nodes can create. Our baseline here is when no temporary channels can be created. And here we're limited to around 250 transactions a second. As you increase the maximum number of temporary channels, throughput scales somewhat linearly. But it starts to tail out at the end because the small nodes, which don't use this optimization, become your sources of congestion in the network. So the takeaway here is that temporary channels help alleviate congestion in payment networks. But if you want high performance, you require high connectivity within your graph. So in summary, we argue that because blockchains are best effort, systems should be designed not to rely on read or write latency bounds for security, but instead they should assume asynchronous blockchain access. In addition, we also argue that because trusted execution environments are not silver bullets, systems must allow for some degree of failures. and we believe that committees complement trusted execution quite well. We have an open source release online, so if you're interested, please check it out. Thank you.
So before you ask question, come closer to the mic and also say your name and affiliation.
Okay, so this is Dong from Shanghai Jiao Tong University, and the question is that, so since nowadays there are many TE implementations like the SGX, SUV, and the trust zone, so I want to know how Teechain can handle the heterogeneity of the TEs. Like SUV does not have the integrity protections, right? So how could you handle this things?
Sure. So, I mean, there was a lot of discussion about this yesterday at the Systex workshop. So the question is essentially, how does Teechain handle heterogeneity, right, within our committees? Essentially, I mean, at the moment, what would effectively need to happen is whoever forms the committee would need to support all the various different differences in the implementations. For example, different attestation models or different hardware security assumptions, right? And at the moment, users would have to make this decision for themselves. But what we kind of see in the next few years, and this was especially relevant for the Systex workshop, is that actually the thought of having some sort of unified model for trusted execution and various different implementations implementing that model, we want to kind of reduce this complexity. So our hope is that within the next few years, we would see various different implementations come around, which would make this easier.
Okay, so thank you.
Hi, Murat, SUNY Buffalo. So chain replication requires reconfiguration when there is a fault, and this requires a consensus box. How do you implement the consensus box, and do you use a committee for consensus box which the members change also?
Okay, so it was a little bit hard to hear you, but is your question effectively chain replication requires reconfiguration on a failure? And how do we deal with those failures?
Yes, you need a consensus box. How do you implement that consensus box? Do the participants of the consensus box also change?
Exactly, okay. So what we do in Teechain is we actually propose a really simple model. We effectively say, if one of the members in the chain doesn't update to the latest state, we force freeze everything. So we basically force the payment channel to be terminated and the state to be flushed down to the blockchain. Now, I agree that actually you can replace this consensus mechanism with any of your favorite consensus mechanism. You obviously just have to take into account what types of failures you want to handle, crash or Byzantine faults.
Got it. Thanks.
Hi, Isaac Sheff, Max Planck Institute for Software Systems. I was wondering if given that one of the examples of traditional payment channels is that two people can issue payments over the channel without having to deal with any intermediaries at the time, and the stated problem with this is that there's some required latency bound when appealing up to the blockchain, could you not do a similar thing for the committees? Have two people settle things in real time, and then in the event that they have to appeal to the committee, there's just some required latency bound when talking to them? And if so, do you lose anything by doing that?
So if I understand the question correctly, you're effectively saying rather than requiring the latency to be enforced by the blockchain, i.e. like some sort of reaction time, you force it within the committee.
Right, instead of forcing every payment through the channel to actually touch every committee member.
Sure, I mean, so you could do that. But the way that we design chain replication is that obviously we took the simple approach, right? Make sure that all members update so you don't open yourselves up to attacks. But I guess this issue, I don't know if I understand the question fully, but I guess if you use like a Byzantine fault-tolerant consensus model where not all nodes need to update, right, you still get your liveness if the number of malicious nodes are underneath your F. Did that answer the question or not really?
Well, I was actually just wondering if you just had the same reaction time problem, a reaction time answer, but instead of putting the reaction time on the chain, you put it in the committee.
No, so we have no reaction times. In Teechain, we explicitly avoid making assumptions about both the blockchain and the latencies of the network. So this might result in cases where the two nodes, for example, Alice and Bob in a payment channel, see different states. But this is something that actually, first of all, you won't violate security, so no one can steal funds. And if they do see different states, the safest thing to do is terminate the payment channel, flush it to the blockchain, and then both parties can synchronize on the state that's in the blockchain. So this is one of the issues actually that we run into with multi-hop protocols. We want to make sure that any conflicting states conflict so that only one true state is flushed to the blockchain.
Thank you.
Okay, let's thank our speaker once more.